and it's counting formulas.
All right, thank you. Happy birthday, Neil. Academically, I was born and raised at Rutgers, and it's a pleasure to come here. And OEIS provided good academic nourishment. So going to OEIS was a regular routine. I would go every day and see if I could find interesting sequences. So thank you for everything. So today, all the talks I've listened to were really inspiring. So I think of what we've listened so far as the pièce of résistance. And now, hopefully, I'll treat you with some desserts. So relax, enjoy the show. This is meant to be fun as much as interactive. So let's go ahead. First of all, the title, Counting Formulas. It's only now that I realize that it's a play on words. How can I get away with counting formulas? I mean, is it formula for counting? Or am I counting formulas? So hopefully I can tell you what I'm doing. So what we're going to be talking about here are formulas for encoding integers. And this was motivated by trying to explain to my then 6-year-old daughter the algorithms for adding numbers. And the algorithm for addition and multiplication were different. And I couldn't come up with a good explanation why they should be different. So what I did is build some ping pong balls and labeled them exactly with these symbols. And the operation we introduced was the addition, the multiplication, and the exponentiation operation. And one of her questions was, well, how many ways can you build a given number? Right? I mean, that was the first question she asked. And I said, you know what? You might have stumbled on your first research problem. So, as a parent, it was my homework to try and work out the answer and guide her to the answer. So, this is meant to be fun game to play with kids. So, a formula in this talk is going to be these trees where the leaves are always ones, and the gates are plus. They can only have two inputs, plus addition, multiplication, and exponentiation. So trying to answer the question to my daughter of what algorithms are in arithmetics, we worked really hard and came up with this picture. That if you really think about all the ways of encoding the number 4, you could actually encode each one of them, and then there are rules that the adults came up with, which they call associativity, distributivity, and commutativity. And these are just manipulations that you're doing on the circuit. So we call this the equivalence graph. You put a graph of all the encodings of a given number, and then you put an edge if there's a transformation which involves either a single commutativity rule, a single distributivity rule, or a single associativity rule that allows you to go from one graph to the other. So from one tree to the other. So for example, to go from here to here, it's a commutativity rule that you use. To go from here to here, you use distributivity, factor 2. To go from here to here, you use the property of exponentiation. So every number has an equivalence graph. And notice, it's very simple to work when you only add input 1. I'll talk about what happens when you add inputs -1 later. It just makes things much more complicated. So for now, what you should think about is the equivalence graph. And trying to answer my daughter's question, I said, let's look at a warm-up problem. Let's think about what happens if you only had pluses. If you only had pluses, I had read in Stanley's wonderful book that this had to do with Catalan numbers. So I could tell my daughter that Catalan numbers are all the formulas you can encode by just using pluses and ones. So she got that. But she said, what about multiplication? What if you add multiplication? I said, it's much, much more complicated, and I went to Dr. Z. I asked Dr. Z that there is this problem quite natural, which has to do with adding, constructing formulas. Can we count them? Can we have a sense of how many formulas there should be to encode a number? And more or less, could we know which one is the most efficient way of encoding? If I wanted to use as few as ping pong ball as possible, what should I do? What formula would I get, and what is the size of this formula? So these questions is what, by the end of the talk, we should have an answer to, if I did a good job. So, as I said, the Catalan numbers just come from looking at the number of ways you can add numbers, construct numbers by using only additions and ones. Now the beauty is that Catalan numbers, we know the formula and we know the asymptotics as we were shown. It turns out that most of the insight comes from the formula. The formula for Catalan number is sort of a light post. And working our way through it, we revisited how you get the formula or you think about it. So the way to think about how these numbers are constructed is to think about what happens at a given root. At root, you either have a plus, or you have a multiplication, or you have an exponentiation. So these are disjoint sets. You can think about trees which are rooted at an addition, or trees that are rooted at a multiplication, or trees that are rooted at an exponentiation. And if you knew how to count each one of them, then you would add these guys up to obtain Cn. Now, as you would expect, the recurrence formula is not linear. It's definitely not trivial, as was pointed out by these facts of Catalan numbers. And this was the recurrence formula for Catalan numbers. But it turns out if you're looking at the recurrence formula for multiplication, there's some similarity going on. Whereas here we had additivity, and this is quite reminiscent of the so-called convolution formula, this looks like the so-called Dirichlet convolution formula, and it counts the number of formulas which are rooted at a multiplication gate. And you could do the same for exponentiation. So if you could solve these recurrences, you would be golden, you would find the answer. All right, so this would have not been satisfactory to my daughter. I couldn't just write this down and say one day we'll find the solution. So we did some number cranking and put the sequence in Sloan. This was my first ever sequence that I contributed to Sloan, so I'm quite happy about it. But we could see one thing right away, that the asymptotics looked a lot like the Catalan formula. The thing changing was the constants involved in the Catalan. So what we were able to show eventually, using properties of generating functions, is that the formula is essentially the same as the Catalan formula, asymptotics, except that the constants are different. And you see, it's not that much greater than 4 if you allowed for exponentiation. And the sequence we contributed to the Sloan sequence is number of formula just using addition and multiplication, and that's the sequence A, 2, 1, 4, 8, 3. All right. So now the next chapter is answering the question, what are the shortest formulas? We now have an idea how many formulas there are. So I have an idea how many vertices should be in the equivalence graph of any number. I don't know how they're connected between them. It's kind of tricky because you have to ask how many ways can you modify any given formula to turn it into another formula. So that's the next project, hopefully when she gets into high school. For now, let's answer the question, how small can you get these formulas to be? So to have a sense of which formulas to pick, you have to have a preference. You have to have some formulas that you prefer and some that you don't like so much. And this actually is a good way of getting into the decimal encoding. Let's think about binary encoding of a number. Well, if you're encoding a number in binary, what you're really doing is writing a number as a sum of powers of 2. This is what I tried to illustrate here. And then, since we can only use 1, we have to expand the exponents as well. Now, it turns out we were beaten to the punch by Goodstein, who investigated these kinds of encoding of integers by expanding the exponent as well. And this actually relates to some of these undecidability theorem that he proved, which connects to what Conway taught us today. So this encoding is the most natural one that comes to mind, but it turns out that it's not efficient. It's not the shortest way of encoding a number. The thing that is prompted right away to a computer scientist is to factor out. And this is exactly what we do with polynomials. When you want to encode a polynomial to minimize the number of evaluation, you use Horner encoding of the polynomial. So it turns out Horner makes your circuit much, much smaller. And I'm going to estimate how much smaller it makes the formula for you. Our favorite formula by far, the one that seems to be efficient, most efficient. So we can show that Horner and Goodstein are definitely there's a difference in the sizes. We cannot quite tease apart the Horner and SCF. We can just show that they're almost optimal both. But we suspect the SCF, which is the second canonical form, to be much better. Let me explain how this works. The SCF encoding essentially amounts to factoring your numbers. So we're going to factor the integers into their prime factors. Now, once you get a prime, you're not done, because you have to express this prime in terms of 1. So you have to subtract 1 to the prime. So the prime is always some number plus 1. And fortunately, that number is a composite. So you can factor it again. So what we do is recursively breaking the primes into 1 plus a composite. So here, 2 is a prime. But if this was 5, it would be 1 plus 2 to the 2. And you would continue until you reach 2. So you do this for the number, the primes, and you do this for the exponent. It turns out this encoding is extremely efficient. However, it's hard to compute. So there's some trade-off going on. Getting the first canonical form is quite easy from the binary encoding. However, to get the second canonical form, you do have to pay the price of factoring your integers. And if they're quite large, it may be quite expensive to do. All right, so these are the 3 encodings. Here's what we're able to show. We're able to show that the shortest formula is lower bounded by log n divided by log 4. We're able to show also that the good thing encoding, the binary encoding, is bigger by a factor of log n. So the amount you save is this factor of log n. The Horner and the SCF, we're only able to show that they're upper bounded by log n divided by 2 times 6, which you can see is very close to the optimum. What we would like to do is say, what's the difference between the SCF and the Horner? And we haven't been able quite to tease that yet. All right. I have to point out that it was conjectured, the asymptotics were conjectured by Zeilberger, and that helped quite a bit in narrowing down the search field. Finally, let me conclude with open questions. At the end of the day, I expect my daughter will discover negative numbers. And she would say, what happens, Dad, if we allow for negative 1? It turns out that all hell breaks loose. As soon as you allow negative 1, even for encoding integers, it might be that using somewhere square root of 2 might make the whole encoding smaller. In other words, the typical example is if you looked at the number 1 plus the sum of all powers of 2. If you allow for negative 1, the smallest encoding is to look at 2 to the power n minus 1. And this is much shorter than adding up all the powers of 2 and encoding the exponents. So adding negative 1 changes the game drastically. So much so that the methods that we've used fail to give an upper bound or a lower bound for the size. There's a trivial upper bound you can get by just bounding the sizes. So what we would really like as answers are answers to these 2 questions. If you give me a formula for encoding n, and you allow for negative 1, well, there are many ways you can create zeros. So you can't just say there are finitely many of them. To get them to be finite, you need to limit their sizes. And the reason I take 2n minus 1 is because it's ridiculous to consider an encoding which is longer than the caveman formula. Caveman formula is 1 plus 1 plus 1 plus 1 plus 1. If you give me an encoding which is bigger than this, I would just reject it. However, if you give me anything else, that'll be good. So if you do that, how many formulas can you get? There's an easy upper bound, but what we really want is a lower bound. The second question was, if you allow for negative 1, how much smaller can you get these formulas to be on average? I would love to get these questions before she gets to high school. I have 4 years. Hopefully I can make it by then. Thank you. Ready for questions? Yes.
We have time for some questions.
Yes.
Did you add division?
Ah, that's a great question. It turns out you don't need division. If you allow for exponentiation, some number to the negative 1 gives you division. You don't even need square roots. So you can actually express solutions to algebraic equations which are solvable by radical. The question is, could you solve algebraic equations which are not solvable by radical by using iterative exponentiation? I don't know the answer, but I suspect the answer is no. I don't know the proof quite yet.
There's another operation too, concatenation.
Sorry?
Concatenation.
Ah, concatenation, that's a good one. So to concatenate, I won't concatenate the trees quite yet, but I would concatenate the Polish encoding. So the reverse Polish encoding has the beauty that it doesn't require parentheses. Because parentheses are a red herring in this discussion. They didn't appear in the trees, why do you need them? So the reverse Polish encoding or the prefix encoding allows you to avoid, and in that case you can concatenate when it makes sense. I don't know what will happen to the numbers in general, but that's a good point. Other questions?
You said we don't need division if we have exponentiation.
Absolutely,
Division
yes.
n minus 1.
Yes,
What
yes.
if we do have exponentiation that we are not allowed minus 1? Do we then need division?
Yes, absolutely. So if you have exponentiation and you don't have -1, then there's no way really to divide, right? Because we only have integers. I just give you 1, and every operation of addition, multiplication that you create just creates integers. So
Does division ever help you make a small?
yes, it does. It does. You just use the exact same argument with the 2 to the n minus 1, and you put it in the exponent. So you encode a to the 2 to the n. So a to the sum of all the powers of 2 less than n. And that is a large number. And if you do the 2 to the n minus 1 in the exponent, you really divide it. You're dividing by a, essentially. Do you see what I mean?
So my question was, if you are not allowed minus 1,
Yes.
still some formulas are very short when you are allowed division. So
I think this is possible, though I don't know. I haven't
did you
checked.
investigate?
Yeah, I didn't investigate that. I should check. I should check. Right. Yes.
In your asymptotics, when you say for almost all integers,
Yes.
these are not the first few exceptions. There
There are many, but the density goes to 0.
Over all the integers.
Yes. So, in other words, the exception of density going to 0 for prescribed epsilon. So definitely I can give you the details afterward of the exact
But
results.
it's important to cite.
Yeah, we have a precise quantification of the amount of
I find it quite evident that the coefficient is close to 4, because when you add exponentiation,
yes, you don't add much.
you just reach a few more numbers.
Sure.
But they are very large.
Sure.
So
But what about multiplication? Quite a few numbers use multiplication, and the prime number theorem would have made me suspect that it might change the asymptotic, but that's not what happened. I mean, the asymptotic changed, but not in the way that I expected it would. Right. Other question? Yes?
So this question at the end, what is the size of the shortest formula when you're allowed to use -1?
Yes.
Did you investigate that in any limited settings, like if you have only plus and times?
So what I did really is to do the naive thing, which is look at numbers that have a certain size and just plug in all possible operations and rule out the expression, the Polish expression, which did not make sense. And that didn't get me too far because the number of possibilities are huge and I couldn't narrow down per integers. So I didn't investigate, what happens if you do different combination of multiplication and addition. And the reason is I was hoping to get a recurrence formula so that I could still use generating function. And that I could say this. So the generating function argument was really due to my collaborators. I'm still looking for a combinatorial proof, one that would use combinatorics or a bijective type identity. And I haven't yet succeeded. So if anybody has ideas how to avoid generating function complex analysis and convergence of series, I'll be quite happy. I haven't succeeded at that quite yet.
You talked about formulas.
Yes.
Is it possible to extend it to the more complicated circuits? Or?
Yeah, so I know how to go from formulas to circuit where you sort of use the efficiency argument. Everywhere where you have 1, you just make it 1, 1. But I don't yet know how to estimate the size of these circuits. So this is sort of giving me some bounds on the circuit problem. But for circuits, the recurrence formula sort of breaks down. So I don't yet know how to handle those as well.
And the minimal, did you try to compute the minimal circuit for small?
No, I didn't. I just computed
So they have sequence.
Yeah, sure. That's a great idea. I'll try to investigate that as well. No more questions? Thank you. You've been a great audience.